So, good evening to all the participants. We are back with the third session for the first day of our international webinar series on applications of mathematics. So, we have with us uh, Dr. Anirban Roy, who is from, Anirban, sir, you are live on
Hi.
screen. Yeah.
Hi.
So he is a faculty member in Christ University, Department of Mathematics, Christ deemed to be University, Bangalore, and he is also an alumnus of GC College. So we are very glad to have him with us. We also have our other speaker, Dr. Bishwajit Dev, who is also there with us. He will also be attending the session. And we also have Manjil Chaikia, Dr. Manjil Chaikia, who will also be presenting tomorrow. The third session will be by Manjil Chaikia. And the second session will be by Dr. Bishwajit Dev. So they are also with us. And we have Dr. Biplab Chaudhary, head of the Department of Mathematics, GC College, here with us. Just a second. Yeah, sir. Sir, can you hear me? Sir, I think, you are muted. Okay. Okay. I would like to thank all the participants for their active interaction during the question answer sessions. And for this session also, I would request the participants to participate in the interactive session by posting their questions and all. And we will take up those questions to the resource persons. Yeah. Yeah. Hello. Yeah, just a second. So we have Bernali.
College Silchar.
Yeah, he will read out the biodata of our speaker. Yeah, continue.
Read out the biodata of speaker Dr. Anirban of this session. Dr. Anirban has been working as assistant professor of mathematics in Christ deemed to be University, Bangalore from 1st June 2010. He did BSc from Gurcharan College, Silchar in the year 1999. He was awarded with PhD in May 2018 from Christ, which is deemed to be University, Bangalore. Dr. Roy has participated 2 times in visiting student research program, that is VSRP, in Tata Institute of Fundamental Research, Mumbai. He has attended mathematical training and talent search MTS program in the year 2002 in IIT Bombay at highest level. His area of research interest includes number theory, topology, linear algebra, differential geometry. Successfully 3 postgraduate students for MTech project, and presently he is guiding one research scholar for his PhD. He also co-authored a chapter in the book Geopolymer Science and Applications. The title of the chapter is Utilization of Iron Ore Mine Waste as Civil Construction Material through Geopolymer Reaction. Dr. Roy has around 8 papers and various articles to his credit. Dr. Roy delivered many lectures in different institutions like the Oxford College of Science in Bangalore, GC College, Silchar, Karimganj Junior College of Science, Assam University, etc. He attended different workshop conferences, etc. He has also participated in a technology workshop on math education organized by Homi Center for Science Education, TIFR, differently Mumbai on January 4, 2019. He has deep knowledge in different branches of mathematics. I may have many mistakes. Please do pardon my mistakes, sirs. Looking forward to an interesting lecture of Dr. Roy. Well, I'm very excited for this lecture. Over to Devashish sir for further continuation.
Thank you, Bernali. Without further delay, I would like to request our speaker, Dr. Anirban Roy, to begin his lecture. So he will start by sharing his screen. I think it's already shared. I'll just add it to the stream. Yeah. So it's visible. So as before, the feedback form will be presented or provided at the end of the lecture in the live chat section, and participants can post their question in the live chat. It will be shown up in the screen at the end of the session. Okay. So Anirban sir, you're up to you. Over to
Yeah.
you. You can begin.
Thank you, Dr. Devashish. Am I audible?
Yeah, audible.
Yeah. And the screen also is being
Yeah,
visible to all, right?
your screen is visible to everyone. Your audio is audible, and your video is also visible to everyone.
Fine.
Okay.
Thank you very much. First of all, on the outset, let me thank the organizer, Department of Mathematics, GC College, and it's a tremendously proud moment for me because I am myself a student of this college, and uh, as this situation is very moment of pride for me as well as tense also because my teachers are also present here. Biplov sir, Dr. Biplov Chaudhary, Jai ma'am. I am a student of them, and today I can sit and talk is the webinar is all because of my teachers. My heartfelt thanks, my gratitude to the college, to the Department of Mathematics, and I'm very lucky to tell that two of them are still there in the department, that is Biplov sir and Jai ma'am. Thank you very much to my teachers, my gurus. Whatever I am, I could do little bit. It's all because of their inspiration, their motivation, and it's a really great occasion, great honor for me. So thank you very much that you thought I could be worth of speaking amongst all the people. I also have to thank before I start the most enthusiastic Dr. Devashish Sharma. Hats off to his enthusiasm. I think he has gone through this COVID, this coronavirus also. He has
Yeah,
been hospitalized.
that's why the program was shifted. Actually,
Yeah,
it was to be
but
held in July.
still
So
he is been arranging all those things. I mean, this itself is a great learning lesson and great inspiration for all of us how to work for mathematics. Thank you, Devashish. Thank you very much. Also, I mean, as I see many of our speakers in this international webinar series, myself, I can see today morning we have attended Dr. Shapan Malik. In fact, tomorrow morning's session I have seen is Jadip Das. We have Dr. Manjil Shaikia, Dr. Vishwajit Dev. So I think Devashish is very nicely spreading the message. What is called vocal for local. So he's organizing a nice session with all the people around us. Thank you very much, Devashish. Heartfelt thanks to you. Thank you to Ms. Barnali also for introducing me. It was embarrassing for me, of course, because you are reading out in front of my teachers. But thank you very much. So here I start with my topic today. The topic for today's session is the tiling of a plane by different polygons. Now, before I start, I want to make sure what was exactly my thought process to organize or to all to organize these slides and preparing this lecture modules. My all intention is that I will consider this session as successful if I can instigate the feeling what I have towards this tiling. This is such a fascination for me to go study about this tiling. If I can instigate that feeling or if I can instigate the excitement to many of the students about this topic, I will definitely consider it's a worth for my effort or my contribution. So I have tried my level best to maintain this session to talk about this mathematics part without entering to the core mathematics. I'll try to make it as much as possible explanatory through pictures without discussing about the core mathematics. Might be certain levels, after all we are mathematicians, we can't escape that. So how the session is planned? The session is planned like that. At the beginning, I will be discussing about the introduction of this concept tiling. What is tiling, why it is, how it is, and then we will slowly enter into the technical part of tiling, and we'll see that first we'll discuss about tilings by this regular polygons. From there, we will go to this tiling by combination of regular polygons, and all the details I'll be explaining just to give a brief about it. Finally, we'll discuss about non-regular, where we'll spend more amount of time, evolution, and the last part, I just kept it as a what are the scopes we can continue with this tiling for the future research. This is about the plan about the today's session. I hope I will be winding up in 1 hour time. I'll try my definitely best, and all your questions, if I can answer all your questions, it will be really great occasion for me, because remember, whoever is asking question, I myself, my teachers are here, again I repeat, so I have to answer. So here I start. So what is exactly this tiles? We see tiles, it's not at all a new topic or new concept for us. Everybody now, whoever is sitting, I probably you all are seeing tiles in your floors. The beautiful floors, if you see today, you see wonderful designs of tiles in the floors. You can see so many designs, and if we think from mathematics point of view, these are nothing but the pure geometry. All these shapes are pure geometry, squares, triangles, all those things are clubbing together to give a beautiful structure of tiles. In fact, nowadays, thanks to the wonderful interior decorations, we see the beautiful bathroom designs. This is my personal favorite of this tiles. So nicely, triangles been clubbed together to give a feeling about the squares. So we see the tiles. Tiles is not something that we don't know or we don't see. We see all around us. And why only in terms of buildings? Tiles we can see in our nature. The mother nature is so great. Look at this giraffe. If you look at the skin of this giraffe, there are everywhere you can see pentagons. So geometry is present in the giraffe. And this is another beautiful things which will come in our discussion in this presentation, the honeycombs. Such a beautiful creations of hexagonal designs here. In fact, you take the examples of leaves, you see the tiles everywhere. This is a dragonfly, another interesting figure, another creature, everywhere pentagonal designs been imparted in that. And particularly where I stand in Bangalore, if you come to southern part of India, early morning they have a tradition of drawing the rangolis outside the home. And when I walk around the different places, it's such a fascinating to see beautiful designs of rangolis. And I see not only the aesthetic view or the artistic view, I see the mathematical beauty on it. Everywhere so many designs, and the fascinating part is the lady or the man who is doing that rangolis might be hardly thought about the geometry about it, but as an output, it's a beautiful display of geometry for me. And this styling. So when you talk about this styling, it is not a very recent subject. It's one of the ancient subject we can see, because we see the tiles not only in the latest interior designs, we see tiles in very early centuries of, you take the Greek example, for example, the ancient Greeks, we see that. Of course, the Greeks, they are the scholars, and they used to claim that you can tile only by triangles, square, and hexagons. Of course, we will see in this presentation, which is not 100% correct. So when you talk about these tiles, if you go to some beautiful creations of historical creation, for example, if you visit Haji Ali Dargah in Mumbai, you will see this particular designs everywhere on that mosque. So nice. If you stand and spend some time in this picture, you will see the geometry is talking to you. And these are something I think everyone will have seen, something called Kashmiri carpets kind of things. So what I mean to say in this introductory part is that tile, what I'm going to talk mathematics about tiles, is not at all a new or a peculiar or unknown topics for me. We see everywhere. And the main objective of my research is that how I can explain these natural things in terms of mathematics. So I'm trying to cover up those those feelings or those thinking in this session, so that after the session, if someone is thinking about tile first time, even they also will wonder, oh yeah, tiles have so many mathematics behind it. So when you discuss about tiling, you can't discuss without this artist. This is a Dutch artist, MC Escher. MC Escher has contributed tremendously in the field of tiling. If you look at this, these are very famous pictures of MC Escher. If you look at these figures now, you will see this. I'm talking about this left design now. In the left design, you see these are, in one instance, I see so many fish. In other instance, I see these are the birds. So fish and birds are clubbed together in a beautiful symmetry. If I concentrate on the right side figure, I see horse riders, brown color as well as whitish color. Brown colors are towards the right of me and white colors are towards left to me. Very nicely this symmetry has come. Of course, I may be wondering, where is triangle here, where is square here, where is hexagon here, then how it is tiling. But actually this is tiling. Most likely I will be able to establish this, what I say, that these figures are nothing but the output of a beautiful tilings. So this artist, this is just the website from where I took these photos. So these are the tiling, or the, I should not use say tiling in this case. These are the creations or artistic creations which very exclusively express the concept of tile. Now, ladies and gentlemen, let me move towards some technical terms. As I said, I'll maintain bare minimum applications of mathematical or technical terms, but certain terms are inevitable to go ahead. Now, what is this tiling or tessellation? In short, a tiling or tessellation is nothing but to cover a plane using polygons, but there should not be any gap, there should not be any overlap. Let's take a look about this tiling. We can see everything is covered if it goes, and there is no overlapping. If I take a look at this, look at that, the full floor is covered, but at the same time no two are overlapping each other. So this is basically a tile. If I take a look at this is another tiling which is much more beautiful, because you can see all the squares are here. In the middle case, it is irregular, or you can say it's a quadrilateral only, whereas the third one is the tiling done by squares, all are of equal size. Another tiling done by equilateral triangles. This is another tiling by triangles, not equilateral. The purpose of giving this 5 tiles is to show that it has been tiled by squares, it has been tiled by quadrilaterals, regular, irregular. We will discuss all those things in this presentation. Now, 2 more terms I have to use. Now, what I mean by monohedral tiling. A monohedral tiling is that if all the tiles in tessellation are of the same size and shape, then it is called a monohedral tiling. All the tiles, what you are doing, it has to be of same shape and size. For example, this tile, if I see, it is been tiled by triangles. So it is a monohedral tiling. If I take a look at this tile, this is also done by squares everywhere. So this is also monohedral tiling. This is another monohedral tiling by hexagons. One more technical term. What do you mean by edge-to-edge tiling? Now, what I mean by edge-to-edge tiling is, an edge-to-edge tiling is nothing but when you take 2 tiles, if any 2 polygons in a polygonal tiling are either disjoint or share one vertex or an entire edge in common, then the tiling is called edge-to-edge. Let me explain this. When I look at this particular tiling, let me take 2 tiles, this particular tile and this particular tile I am taking. I'm sure you can see what I am making mark on the screen. The tick mark, what I am doing, is it visible to you? I hope it is visible to you. Okay. Can I get a confirmation that whatever I'm writing on the screen, is it visible to others?
Yes, Anirban sir, it's visible.
Yeah. Thank you very much, Dr. Devashish. Thank you very much. Okay, so let me come back. Yeah, so when I take these 2 particular tiles, you see their intersection is disjoint. They don't have any intersection. But let me take this double tick, this one and this one. When you take these 2 tiles, they have an intersection which is nothing but this common edge. This common edge is the intersection. Whereas if you take this tile and this tile, the intersection is not an entire edge, it's a half of the edge, right? So what is this edge-to-edge tiling? Let's focus on the third case here. In this third case, you don't see any 2 tiles whose intersection is half of the edges. whenever two hexagons are meeting, they are meeting in exactly a full side of the hexagon. So this is an example of edge to edge tiling. This is the example of edge to edge tiling, because whenever they are intersecting in a full edge. Whereas if you take this example, this particular triangle and this particular triangle, though they are intersecting, but they are intersecting in half of the edge, or they don't have a common vertex as an intersection. So what is an edge to edge tiling? An edge to edge tiling is whenever two tiles meet, either they are disjoint, we don't mind if there is nothing common between them. But if there is something common, it has to be either a vertex or it has to be an entire edge, not a half edge like this. We don't allow this kind of intersection in an edge to edge tiling. So we have introduced two terms. One is monohedral tiling, where all the shapes are equal, and we have considered edge to edge tiling, where intersection is a common edge. With that, let me come back to these figures. So when I take these tiles, this is an edge to edge tiling, as well as this is a monohedral tiling. So if anyone have a doubt in the mind, oh, what is the difference between monohedral tiling and regular tiling? Because by the term regular, we understand it is nothing but having same size, all the sides are equal, as well as all the angles are equal. So in monohedral, they are telling that all are same size and shape. But in a monohedral tiling, individually they don't have to be regular, right? If you look at this particular tile, it's a tiling by quadrilateral, whereas none of these quadrilaterals are regular, but overall it's a monohedral tiling, as well as it's an edge to edge tiling also. This particular tile, it is done by again quadrilateral, and it is an edge to edge tiling. This is done by equilateral triangle. Now this particular example, friends, this is the tiling which is a monohedral. It is an edge to edge. Moreover, it is regular also, because all the triangles are nothing but equilateral triangle. All sides equal, all angles are equal. Whereas this triangle tiling, it is not it is not regular, because all triangles are not equilateral here. So I have introduced two particular terms, that is monohedral tiling, edge to edge tiling. Now let me come to the topic of regular polygons, which was the second part of the session. Question is, if I need to tile with regular polygons, whether it is equilateral only, square only, hexagon only, or I can have more. Let us take a look at this. You take any n-sided polygon. If you take any n-sided polygon, that can be divided by n-2 triangles. What I mean by this, here we have a pentagon, that means a polygon of 5 sides, and we have divided into 3 triangles, 5 minus 3, so you have divided by 3 triangles. You take an hexagon here, that is a polygon of 6 sides, you divide it by 6 minus 2, that is 4 in 4 triangles. We take an heptagon here, that is a polygon having 7 sides, 7 minus 2, 5. You can see 1, 2, 3, 4, 5. We have exactly 5 triangles. So what I've written here, that if an n-sided polygon is there, you can always divide it by n-2 number of triangles. And the sum of angles in a triangle is equal to 180 degree. So what is the total angle of this any polygon? It is nothing but n-2 into 180 degree. So here I'm getting the formula. Of course, we know this formula. So whenever there is a polygon of any number of sides n, the total sum of the internal angles will be equal to n-2 into pi. And this n has to be greater than or equal to 3, because if there are 2 sides, you don't get a polygon. A polygon starts from 3 sides, that is a triangle after all. And this result is true for the regular or irregular. So once we have this total angles, now we want to see what about the regular polygon. Now regular polygon means all sides are equal and it has exactly n number of sides. So what you get? You get n-2 into pi divided by n. So each angle, whenever it's a regular, we can talk about each angle. Whenever it is not regular, we don't have that liberty to talk about individual angles. So when we have a regular polygon of n sides, each internal angle is equal to n-2 into pi divided by n. Now what we told is the previous slide is that a regular polygon, that is an equilateral triangle, a square, and a hexagon are going to tie. Let us see how they tie. So each internal angle of an equilateral triangle is 60 degree. And what is the definition of tiling? Tiling says there is no gap, there is no overlap. So when 6 triangles come together, take a look here. When 6 triangles come here, inside this circular thing, you can see 6 triangular edge, vertex. So when you take these 6 triangles, all 6 are meeting at one common point here. That is the definition we studied now for edge to edge. Intersection should be a vertex or a complete edge. So 6 triangles will always tie. 6 equilateral triangles will always tie. Let's see about the squares. Each angle of square is 90 degree. And when 4 squares come together, you get a here complete round 360 degree. Similarly, when you take an hexagon, each angle is 120 degree. So 3 into 120 gives you 360 degree. So even hexagon will also tie. So it is no doubt that an equilateral triangle, a square, and a hexagon will always tie. What about other polygons? Next polygon like pentagon, will that tie? Let us see. So these are the 3 examples that are the only regular edge-to-edge monohedral tiling of the plane. The question is why? Why I use the word only? Why not others? Let's take a look here. Now we are considering a regular pentagon. Pentagon means 5 sides. So 5 minus 2, 3, 3 by 5 into is nothing but 108 degree. Now when you have 108 degree, if you take 3 pentagons together, what you get? You get 3 into 108, 324 degree. That means a shortage of 36 degree. So there will be a gap. In tiling, gap not allowed. Now let us take 4 pentagon. If I take 4 pentagon, you get 432 degree. And then you get an overlap. Neither gap nor overlap is allowed in a tiling. So naturally, this regular pentagons will not tile. So whatever way you arrange it, after all it's a regular structure. So whatever way you arrange it, you're always having a gap of this 36 degree, or you will have an overlapping. So conclusion is that regular pentagon does not tile. What about other pentagons? Pentagon of 3 sides tile, that is triangle. Pentagon of 4 sides tile, that is square. Pentagon of 5 sides does not tile. Let us see pentagon of 6. Yes, that also tile. What about 7? So quickly let me note down all these polygons up to size 10. If you look at each of the internal angles, see 128.6, it will never ever club to give 360 degree. 135 will not give. 135 is 270. There is a shortage of 90 degree. 140 is 280 degree. Again a shortage of 80 degree. 144 is 288. Again a shortage. That means if unless and until you have an internal angle which is coming out as a divisor of 360 degree, it is not possible to tile them. So conclusion is what? Conclusion is that whatever you take, we observe that angles at each vertex will not add up to 360 degree. So what is the conclusion? No other regular polygons admits monohedral edge-to-edge tiling except regular triangles, that is equilateral, regular quadrilaterals, that is squares, and regular hexagon. So this is about the regular polygons. We don't have much more things to study here. But so far what we did, we have considered only one type of tiling. Actually, these are known as Euclidean tiling, what we have seen just now. Now let us allow the combinations. I will go a little bit fast in next 4 slides. What I mean by combination, if you look at this tiling, it is a 3 triangles and 2 squares are tiled. Here it is 4 triangles. If you spare time, you can understand 4 triangles and 1 hexagon has been tiled. Here 1 square, 1 hexagon, 1 dodecagon has been tiled. Here you have taken 2 squares. You can see these squares here. These are the squares. 2 squares, 1 triangle, and 1 hexagon. This pink color is 1 hexagon. Similarly, if you take here, you have 1 triangle and 2 dodecagon. The big circle. Actually, they are not circles because this picture's been merged together, so it looks like circle. Then 2 triangle, 2 hexagons, and 3 triangles, 2 squares, and 1 square, 2 octagons. These 8 tilings are known as known as Archimedean tiling. This is Archimedean tiling existing from probably from the beginning of century. And in fact, we'll come back to this tile chapter, this slides once again. Now I want to show quickly how it is tiling. So you take 3 triangle, 2 squares, each angle 60. So you take this combination 3 into 60 plus 2 into 90, you got it. You see here, I just want to show that where are the 3 triangles. One triangle, another triangle, another triangle. One square, another square. You have 2 squares, you have 3 triangles, club them together and all are regular. You get 360 degree. That means there is no gap, no overlap, successful tiling. Similarly, when you take 4 triangle and hexagon, you can easily get 4 triangle, 4 into 60, 240, 1 into 120, you get successful tiling. Here you have 1 square, 1 hexagon, 1 dodecagon. That means square means 90, hexagon is 120, and dodecagon is 150. Club them together, you get 360. You are able to do this. Similarly, when you take 2 square, 1 triangle, 1 hexagon, you get that 3 triangle and 2 squares, and finally you get 2 triangle, 2 hexagons. You are getting this, right? So this is all about that, how when you combine regular. Now, interesting questions. These are not monohedral tiling, because for monohedral tiling, each tile have to be same shape and size. No doubt these are edge to edge tiling, but they are not monohedral tiling. Now, lastly, if you take that 1 square in octagons, octagon generally we don't see much more. Octagon means individual angle is 135. Successfully they club. You have 2 big octagons, 1 octagon here, 1 octagon here, 1 octagon, 1 octagon, and 1 square. So you get successfully no overlap, no gap. And if you take 1 triangle and 2 dodecagon, dodecagon means a polygon of 12 number of sides, successfully you get. So when you are allowing combinations of regular polygons, you can tile, but they won't be monohedral. So where exactly we stand? What is a tiling? Okay, we understood. No gap, no overlap. Tiling has a partition like monohedral as well as edge to edge. If you take only regular tilings, yes, you get monohedral edge to edge if it is only 3 types of regular: triangle, equilateral triangle, square, and hexagon. If you combine regular polygons, you have the set of Euclidean tiling. Now, what you do? Finally, you once again, I think the title is showing combination of regular polygons. So finally, if the regularity condition, so now what you want to do? We want to drop this regularity. We don't want regular anymore. So what are the polygons are possible? Because if you remove the regularity, you have seen that angle when the vertex are coming together. If it is regular, means you have no choice about the angle, it is fixed. But if it is not regular, you can adjust it, right? You can take any triangle and we can adjust it. So this is the question that has been striking people. And to be very precise, this is the question mathematicians have been trying to get answer from 1910. If I can put it in a proper format here, yes, it is 1910. And during my presentation, this is the story or this is the history which I'm trying to convey to all of you. So when you have a convex polygon, another important term, the third technical term I'm using after monohedral and edge to edge, I'm talking about the convex. Now, mathematically, you know what is convex definition. I'm not interested about mathematical definition. I'm talking about geometry. So what is a convex? Convex polygon means angle is more than 180 degree. Like in this figure, you see, these are the quadrilaterals which are convex. Why convex? You take 2 points and join them by a line. The line is not in this quadrilateral, it is outside the quadrilateral. So it is not a convex. So in this presentation, in this discussion, we are in convex. Whatever polygon we will discuss, it is convex. Okay. So this is one assumption we have taken, that we are discussing about the convex polygons. So now, what is the work? The work has come that classification of all convex polygons that will tile the plane. Now, the moment you said polygons, there is no restrictions about regularity. And take a triangle. You take the midpoint of the triangle and rotate it by 180 degree. You see, you are getting successfully tiling done. and these are edge to edge, and these are monohedral indeed. You take the midpoint of that and you rotate it, you get another, you rotate it, you get another, like that, right? So naturally this triangle will come to this, or you can say this triangle come to this. Ultimately you are getting a successful parallelogram tiling. Same nature for quadrilateral. Only thing is that take each side, take the midpoint and rotate it by 180 degree. You will get this kind of tiling. These are monohedral tiling because they are all maintaining same shape. The moment you decided one quadrilateral means you are done with the amount of angles, sides. You need to repeat it. So these are monohedral, these are edge to edge. So triangle and quadrilateral, no issue. That means polygons of size 3 and polygon of size 4, no issue. But the game starts the moment you come to pentagons. When it is a pentagon, there's a huge complexity. Let me take a pentagon where angles are this 100 and 140. This is the pentagon. Okay, four angles are 100 degree, one angle is 140 degree. Whatever way we try to bring them together, 100 and 140 will never give 360 degree. However combination we think. Let me show all the combinations. You can club, you can bring 140, 140 together. Means I can draw another polygon pentagon here, which angle is 140. But if you take 140, 140, you will have 80 degree deficit. And 80 degree is not supported by any of this. If you take 100, 100, 140, that means only 100 already there. I take another 100 here, I take another 140 here. You will have some gap here. 20 degree gap will be there. Or you take all angles are 100 degree, means this is 100, this is 100, this is 100. You will again have a gap of 60 degree. So this pentagon will never ever tile. No matter how we try to put these pentagons together, we will always end up with a gap smaller than the available angle. So it is not going to tile, neither monohedral nor edge, because it's not a tiling after all. So where from monohedral and this comes. So automatically a question comes, okay, this pentagon does not tile. I can find different combinations. And this is why I told that this lectures, now if any students are here from the school levels, they will find highly interesting because you don't have to know higher mathematics. Okay, it is good enough to have a good sense or knowledge about geometry. You can easily find out some combinations. Let me show one combination where it is tiling 90, 90, 90 and 100 and 170. You can easily club them 90, 170 and 100. It gives 360 degree. That means this pentagon should tile. But the game is not so simple. This pentagon will not tile. We will see what is the problem. That is why the pentagon is so interesting. Well, I have taken this pentagon ABCDE where the sides, 3 sides are 1, 2, 3, 2 sides I kept as variable x and y. Angles are given, 3 angles are perpendicular, one is 100, one is 170. Now, when I solve this triangle and try to find out the values of x and y, we may come across these values of x and y will be irrational numbers. Means, however accurately you draw, there will be an error. It is not possible to draw. Because 100% irrational figure where from you get. But we are talking about the clubbing. So what happened? We try to bring 2 pentagons across the side of length 1. That is the side AB. Let me show the figure here. So see, I brought 2 pentagons as an edge to edge, satisfying the edge to edge restrictions. So this AB, I'm trying to tile it across this side AB. What happened? 1670 degree, 170 degree is 340 degree. Now there is a gap of 20 degree. Who will fill up that gap? This pentagon cannot fill that gap because it does not have any angle of 20 degree. That means in this way you cannot tile. Let's see other way. Instead of clubbing like that, let us tile in this way. So this is a successful tiling. Why successful tiling? What is the angle ABC? It is 90 degree. This angle is 90 degree. What is the angle BAE? You can see here BAE is 170 degree. So here you have 170 here. 170 plus 90 is a 260 degree. Still we need 100 degree. And 100 degree is supported by this pentagon. So another pentagon can easily pitch in here and it can fill up the gap, right? This is what I've written here. Left one creates a gap of 20 degree, right one gives a chance of 100 degree. But the side will come into picture now. Let me show what exactly happens. So this is what I was showing. This is going to tile, but size is creating trouble. What I mean by trouble? Dear friends, when you bring a third pentagon having to satisfy that angle becomes, you know, what I was telling, that this angle is 90, this angle is 170. So 90, 170. So this angle has to be 100 degree. That is DEA. In this figure, if you see DEA, yeah, it is 100 degree. So successful tiling done. There is no gap. So what is the problem? Problem is, if you take the intersection of yellow pentagon and blue pentagon, the intersection is not an entire edge. Intersection is some part of the edge. So it is giving me a monohedral tiling, but it is not giving me an edge-to-edge tiling. So there is a problem. You are able to do tiling by this combination, but it is giving a monohedral only, not the edge-to-edge. So neither of these arrangement, this thing. Now I move on. So there is the final conclusion about the pentagon is that pentagon is a complicated nature. But we have shown only 2 examples. From 2 examples, we cannot say that it is not possible to tile. In fact, a strong intuition says that there are infinite possibilities should be there. Because only by 2 options we try. So there should be an infinite possibility where you can bring irregular pentagons together to make successful tiling. Even the tiling can be both monohedral as well as edge to edge, or it might be it is not edge to edge. Monohedral always, because you are taking only same kind of pentagons. Because pentagon has a beautiful nature, that is pentagon, when you bring its sides and its angles, they are related to each other. Pentagon sides and pentagon angles are related to each other. So you twist the side, angle also will be twist. They are interrelated to each other. So pentagon is very complicated. We don't know how many pentagons are there, but we strongly feel there must be pentagons which will tile. So what do we do? We remove one condition. Let us relax the edge to edge restriction. If you relax this edge to edge restriction, look at this tiling done by rectangle. It is an edge to edge. But if I don't consider edge to edge tiling, then this is the figure you get. And why to stop here? It will give us infinite possibilities. We can tile like that because we are not more restricting to edge to edge. But if you restrict to edge as well as monohedral, you have one and only tiling done by the rectangles. So question comes now. It increases the complexity with pentagons for finding the right combination of sides and angles even when edge to edge condition is relaxed. So this is the problem which took exactly 100 years. Actually, to be more correct, I should say 110 years, because it all started in 1910. And till date, it has been found that it is 15 pentagons and 3 hexagons, and that's all. We cannot have anything more than that, which is going to tile. What I'm going to discuss in the next time is that this is mainly, this research has started, I should not say research started, the first finding was available in 1918, and then it took 50 years for the next, that is 1968, but only that particular group of people who are doing about it. Then one article came by Martin Gardner in 1975 in their Scientific American magazine under the column Mathematical Gains, where he has nicely explained about the evolution of number of pentagonal tiles till that date. And that article created a lot of interest among people. Even the people don't have to be a mathematician. That article created interest among mathematicians, non-mathematicians. So I will basically, what I'm going to show now, I'm going to give you that evolution, that historical evolution, how the tiling concept developed, and how people reached to the conclusion that only 15 pentagon and 3 hexagons. This is what I'm going to show. It is mainly copied from the idea of Martin Gardner, but Martin Gardner did up 1975. There are a lot more discoveries after that. So I have covered that complete history or complete journey of tiling's evolution. In short, what is the journey? It all started by Karl Reinhardt in 1918. It took 50 years. Then in 68, Richard Kastner. Actually, this Reinhardt, he has proved that you can tile a plane by only 4 types of polygons, that is equilateral, that is triangles, not equilateral, any triangles, any quadrilaterals, any pentagon, but total possibility he told only 5, and 3 hexagons. It took 50 years, then Kastner has added that no, it is not only 5 pentagons, I can add another 3 more variety. After 68-75, Richard James, he was not a mathematician, he was a computer scientist. He has also contributed by giving 1. And then the beautiful story of this Marjorie Rice. This Marjorie Rice, she has contributed by telling another 4 types of pentagonal tilings. And the interesting part, Marjorie Rice, no way related to mathematics. She was looking at the homework copy of her son one day and came across to that particular magazine. And that started her interest. And just by pure intuition and creativity, she has come out with many, precisely 4 pentagonal tiles. We will see in details about it. After Marjorie Rice, Rolf Stein, he has also contributed 1 more. And then quite a gap of there, almost, you can say 30 years, 85 to 15, yeah, 30 years. So these 3 people, MacLeod and David von Derau, they have given 1 more. But none of them have said that these are the all. If you tile a plane, it has to belong to these 15 pentagons. That statement nobody told. In fact, I find it interesting to mention this Kastner, he has not given the proof of his discovery also. And as a reason, why proof is not given? He has given a very funny statement. He said that if I have to give the proof, the paper will become a book, which he does not want to make now. Just because of space constraint, he did not give the proof. So in fact, this is a very interesting case for the school students who are up to class 10. They can take up this challenge. They can prove that how they are going to tile. We will see in details about it. But recently, only 3 years back in 2017, Michel Rao, another computer scientist come mathematician, he has proved using algorithms and programming that no, however you try, you cannot have any more variety of pentagons. Only 15 pentagons is going to tie, only 3 hexagons going to tie. No other pentagons will tie. Even though if any other pentagons tie, it must belong to one among these 15 pentagons. Now let me quickly go through about this one by one, how and what is the pentagon they have given. So to start with Reinhardt, I have to mention something about it here, some interesting story. It's very tempting. In 1900, there was the International Mathematics Congress, International Congress of Mathematicians in Paris, which is a very prestigious conference. There, David Hilbert, he has given a public talk, and he has posted total 18 number of open problems. Out of this 18 number of open problems, the 18th problem in precise was that, however you try, you can never cover a plane by polygons. Okay, so what Hilbert told precisely, not exactly this statement, precisely what he told is that however you try, you will not be able to cover a plane. Actually, he said you cannot be cover a plane by fundamental groups. Well, I want to avoid that mathematicals here. So he said precisely, however you try, you will not be able to cover a plane by polygons. So when this Reinhardt came for his PhD to this Biberbach, or Biberbach, how you pronounce it. So when this Reinhardt came to this Biberbach for his PhD, Biberbach was attending that public talk by Hilbert. Instantly he told, why don't you take up this problem? So they decided they will work on determining the convex domain which can tile the whole plane. Okay, so see the beauty, it was an open problem, but they just took it as a PhD work. Okay, and they did the partitioning of the plane into polygons. And it took 8 years time for Reinhardt to complete his PhD thesis. And as a thesis, what he has done, he proved that a convex M-gon can tile the whole plane by identical copies, that means you're talking about monohedrality, only if the number of sites are less than or equal to 6. So that was a revolutionary discovery. It immediately ruled out all those heptagon, octagon, dodecagon. No need to discuss anything. We discuss about triangle, quadrilateral, pentagon, and hexagon. Triangle, quadrilateral, intuitively, automatically they tile. I mean, we just matter of rotations, you get the tile. But pentagon, we don't know what are the pentagons will tile. Hexagons, we don't know what are the hexagons will tile. But in Reinhardt, in his thesis, what he has given all the list. What he has given, he has listed out what are the 3 hexagons that are going to tile. That means you take any tiling by hexagon, it has to belong to one among these 3 hexagons. Let me quickly show you what are these hexagons. So this is the first type, where sum of 3 angles is 2 pi, A, B, and this C. They will put together 2 pi, and the sides A and D will be equal. This is the overall picture of tiling. Here I am showing as an individual plot or individual tile, and here is how the overall tiling look like. Point to be noted, these are edge to edge tiling. So now I will just quickly run through all the variety of hexagons. This is the next hexagon type, where it is given that A plus B plus D is 2 pi. A plus B plus D is 2 pi. Side A and side B are equal. Side C and side E are equal. This is how the tiling look like. And the third type he has given like this, where A, C, and E, each one are is equal to 120 degree. Side A and side B equal. Side C and side D equal. Side E and side F equal. That means out of the 6 sides, pairwise they are equal. So if you tile by hexagons, you can tile only by any of these 3 hexagons. If you change the condition, you may not have a successful tiling. Or if you are able to tile by another hexagon, it has to belong to one among these 3 hexagons. It's a wonderful result. And the proof is always a question mark. That means, can I say that this proof is completely done? Well, many articles has been published about saying that yes, the proof is done and they have given proof, but still people are working. In fact, I also one among them. My student also working. Anybody wants to start working on the tilings, it's quite interesting to check out how they tile, why they tile. So here from hexagon, I move to pentagon. Reinhardt, he has given 5 types of pentagons. Okay, that is in 1918. He has given 5 types of pentagons. What are the types? When I draw this, my dear, you can all see that there is a similarity of this tiling with the tiling given by hexagons. Right? That means when you take an hexagon, this pentagon, some of the pentagonal tilings are nothing but as a corollary, it is derived from hexagons. So let me run through quickly about these types. Here A plus B plus D 2 pi and A equal to B. This is the similar thing we have seen in hexagon. Only it is pentagon. And each angle is, not each, 3 angle is ACD is 120 and A and B are equal, and there is a change. That time it was pairwise equal, now we have only 5 sides. One side is equal to sum of the remaining 2 sides. If you take the side C and E, they will contribute to D. This is the tiling. So there are 3 pentagons. Next one, you take the type 4, where 2 angles are 90 degree, A and C are 90, and side A equal to B, side C equal to D. This is how the tiling look like. Similarly, the 5th type is A is pi by 3, C is 2 pi by 3, A and B are equal, C and D are equal. This is all about the 5 types of pentagon given by Reinhardt in 1918. From then, it took 50 years time, and then came Kastner, who has discovered 3 new classes. These are the 3 new he has given. So point to be noted, we have now 5 plus 3, 8 types of pentagons. What is this pentagon? A plus B plus D will give 2 pi. Angle A is nothing but double of angle C, and A, B, E, they are equal, whereas C and D are also equal. Not all are equal. It can be all equal. If you make all sides equal, that will lead to equilateral pentagon. We have some interesting problems based on it. This is how the tiling look like. Next one, of type 7, we have 2B plus C, 2 times B and C. Similarly, 2 times d plus a, and that sum gives you 2 pi, and 4 sides are equal. Only one side is not equal. The fifth side can be equal to them, need not be equal to them. Last one given by Kastner, almost similar. This time 2a plus b and 2d plus c, and a, b, c, d are equal. This gives the total 8 number of pentagons. After Kastner, it came Richard James. Richard James, very nicely, he took it as a challenge. He read basically that Martin Gardiner article, and he started finding by himself, and he decided, I won't look at what are the existing pentagons. So without referring any of these 8 pentagons, he started working out about this, and he applied a very nice technique. What he took one of the Archimedean tiling. I mentioned about this Archimedean tiling earlier. Archimedean tiling means here is the Archimedean tiling, and he took mainly this particular tile, that is 1 square and 2 octagons. He took 1 square and 2 octagons, and what he did, let's see what he did. He has just divided 2 sides from their midpoint by perpendicular lines. What exactly he did, that is the pentagon he got, and according to him, E must be 90 degree. A and B should be complementary to each other. 2 times B and difference, that should be 2 times C plus D, which should give you pi. And the side B and D, side B plus D should give us A and B. Now what exactly it is, intentionally I kept this open. You see, this is an octagon. 1, 2, 3, 4, 5, 6, 7, 8. At octagon, you take the midpoint and divide. Take the midpoint and divide. Take the midpoint and divide. You come across 4 pentagons. 1, 2, 3, 4, and there was a gap, that is by square. Club together, you get 5 pentagons, and you get a nice symmetrical structure. So that is another pentagon, number 9. So we have now 9 pentagons. Then it is Marjorie Rice. I have already mentioned about the story of Marjorie Rice. Another person who got excited by seeing that Martin Gardner's article, and just as a challenge and applied her creativity. She has given 4 types of pentagons. 9 plus 4 list goes to 13. But nobody told my is the enough. After that, no more pentagon. That nobody said. So what are the pentagons given by Rice? Rice is given like that. I think I should be a little bit fast now. Rice is given like that. And another type where A is 90 degree, C plus A like that. The figures are quite self-explanatory. 2 more. Pentagon number 12, where A is 90, C plus E is pi. 2 times of B plus C is a 2 pi, and 2A is going to be equal to C plus E, which is equal to B. And the last pentagon given by Marjorie Rice. This Marjorie Rice story is so beautiful. That lady unfortunately expired in 2017, and in her memory, I think it was International Mathematical Society somewhere, they have created one big tiling given by this Marjorie Rice and just kept it in her memory. And this is a very nice story. I mean, you can always find it. Well, finally, let Rolf Stein. He has also contributed after that one more. He has contributed another one. And lastly, these 3 gentlemen, Anne McLeodman and Van Doreau, they has given this. This is almost very specific, angle A, B, C, D, E. Individually, they have fixed the measurement. And they told this is the tile you are going to get. Okay, so this makes the list of 15. All the research work started from 1910 when Reinhardt met B. Berbach, and it took 2017, that is exactly 107 years, that means 1 century, more than a century, to conclude that yes, these are the things. And this Michel Rao, he concluded with the theorem after testing more than 371 cases. He has concluded that these 15 are things. But point to be noted here, till date, no mathematical proof is been found that these 15 are the exhaustive list. Of course, using computer program it has been found, but mathematically still it remains an open question that 15 pentagons are the exhaustive list. All right. So this is a summary what I have shown here. 18 Reinhardt, 3 plus 5, and Krasner 3, 5 plus 3, now 8 pentagons. Then Richard James, 1 more, 9. Finally, Marjorie Rice 4, 9 plus 4, 13. Then Rolstein, another one, 14. And lastly, these three gentlemen, total 15. Marjorie Rice concluded the journey. He said, stop, there is no need of further searching. This is the history of the evolution of these pentagons. So what I have explained so far is that I told about the tilings. I told about the tiles, how it is found in nature, and one of the basic urge of taking up this topic for study is to explain the nature. And this is the journey in tiles so far in the history of mathematics. Now, how these tiles are being used in nature. Remember, we have shown in the beginning that M.C. Escher's painting. So tessellation by equilateral pentagons. Now here it is equilateral pentagons. That means pentagons, but each sides are equal. Okay. When you take equilateral pentagon, that will fall under type 1. It may fall under another category also. In fact, it will fall under another 2 category. I have taken the first category. So if you take the first category, what happened? You take 4 of the pentagons together. Okay. Quadruplets of these pentagons can be grouped into oblong hexagons in 2 different ways, and this is the tessellation given by M.C. Escher. It's a beautiful tessellation. I mean, she has given, it's called starfish, shells and starfish. You can see starfish as well as shells. You can see shells, you can see starfish. It's all are there. Starfish, 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 1 starfish here, and then 4 shells. Similarly, again, you can see starfish, starfish, and then 4 shells, right? And this is a beautiful picture depicting by this thing. Now, if I go back to that, when you look at this left side, my dear friends, when you look at the left side, it is a quite visual art. If you look from close, if you take your eyes back, you can see that they are pentagon, pentagon, pentagon. You can take it as a 4 like that, and you get something. It overall creates a symmetry. This is what M.C. Escher used in most of his paintings. You see, when you look at this, in first impression, it's a fish. In second impression, no, it's a bird. Here, first impression, all the horses are going right, but no, all the horses are going left. There are some different 3-dimensional art also in this. In fact, a couple of years back, there was an exhibition in Bangalore, NCBS, of this paintings by Escher. So these are wonderful designs. I come back to this. So, okay. So this is how you are explaining that M.C. So there is some much more work I have to mention about it. This is called Metamorphosis 2. It's one of the famous painting by M.C. Escher. And in this, if you spend time to understand, everywhere you see the interesting part of symmetry. Left, right symmetry. Here, birds are flying. Another way is down. So everywhere you see symmetry. These are nothing but falling under. I have just shown in one example where this famous painting by Escher of starfish and shell can nothing but type 1 of pentagon. Similarly, all these metamorphoses or any other paintings each belong to one among these 15 types of pentagons. Moving from art, come to the nature. You see these tiles. It is a tile of type 2. And this is actually look like fish. So many fish are there, right? So this beautiful picture of fish is nothing but pentagon of type 2. So all these fish we see in nature, and when you bring all the fishes together in a net or somewhere, it is nothing but a beautiful creature. You think of the bees in clover. Bees in clover is another type which belongs to type 9. In fact, this is the type given by Marjorie Rice. And these figures, what you are seeing here, these figures are taken from the Marjorie Rice article, what she wrote. I have cut paste the figures from Marjorie Rice article, which is for all public. Lastly, one more I'll show and then I stop here. The beautiful butterflies. So nice, so fascinating. These butterflies are nothing but the symmetry. If you take the mirror image, if you look at this, if you focus on this kind of thing, it is nothing but mirror image of each other. Butterfly also is nothing but the mirror image, right? Mirror image of each other. So beautifully these things are nature. Now here, just for time constant, I have taken only 3. We can, there are ample. And as we mentioned about the scope of research, everything can be explained. Now, my last, as I mentioned, I think so far, as I told, 90% or 95% to understand this, you don't have to do any higher mathematics. So far, whatever I have explained, it is purely about our normal knowledge up to class 10 is more than enough. But in this, we are talking about geometry, then how can you keep topology away from it, right? Topology means nothing but topos logos, that is surface study. So naturally it comes. I will go much more fast here just to show the conclusion of the problems here. So there is an article by this Grunbaum in 1980. What he has taken, each tile they have considered as a topological cell. Okay, they have considered each tile as a topological space. So when you're talking about a topological space, tiling is nothing but covering of the space such that interiors of the tiles are pairwise disjoint. Basically, two tiles is what? They are either disjoint and they have only one intersection, either vertex or the common edge. So in terms of topology defined, this is nothing but a closed cell. You all know that, right? Closed disk. Now, down the line, in very recently, Teruhisa Sugimoto, Japanese mathematician, in 2018, they have proved that if you are talking about a convex pentagon and the pentagon will be, if it is a periodic tiling, this is something I have not discussed. If it is a periodic tiling, then a sum of any three internal angles will be 360 degrees. Now, what do you mean by periodic tiling? Periodic tiling means a tiling where one tile can be translated onto itself by two non-parallel direction. That means if you have a tile here, friends, it can be shifted to right side, it can be shifted to left side, it can be shifted to up, it can be shifted to right. If this is one transformation and this is one transformation, these two transformations are non-parallel transformations. If you rotate it or magnify it, then it is no more a periodic tiling. So under that, this is, I mean, you can just skip what I'm going to show now very fast. So this Sugimoto, what they have given, they have defined some new terms like what is called a normal, what is balanced, and they defined these terms. And finally, they concluded that if you have a strongly balanced tiling, then they have given a result also. But point to be noted, what I'm trying to show, already I have shown you about the periodic tiling. And when you talk about periodic tiling, there is a question of non-periodic or aperiodic tiling. That lays the ample scope of research. Now, when you talk about aperiodic tiling, taking from this Sugimoto's inspiration, if you are discussing about an aperiodic tiling, then what about the sum of the angles? Whether sum of the angles will be equal to 360? And this gentleman comes into picture very fast. This is nothing but Roger Penrose, Sir Roger Penrose, who has given first time, okay, I should not say first time, he has given the idea of aperiodic tiling or non-periodic tiling. Sir Penrose, what he has done, he has given this kind of tiling, which is called Wang-like dominoes, that means squares given by different colors. And what he has taken, he cut the rhombus in such a way that angles are 72 and 108 at each side is equal to golden ratio. Then these things will create a periodic tiling, because if you have to merge two, suppose you want to take this end to somewhere, moment you shift it, you see, you cannot merge them together. What you need to do, you need to either deform it or you need to stretch it, or you might have to rotate it. So that is the starting of aperiodic tiling in the year 1974. And as the days goes, more and more inventions have started coming on aperiodic tiling. In aperiodic tiling, very recently, a great discovery is that arrangement of atoms in quasi-crystals. In quasi-crystals, you are seeing this aperiodic tiling. So it is possible to create infinite number of aperiodic tiling based on this concept. Okay, to go further, I mentioned about Hilbert lecture in that international congress. Hilbert once told that he just tried to define what is a good problem. So according to him, a good problem is a problem if you explain to anybody on the road, they should understand. And this is a nice, good problem. Whenever we go to market, we see, all the fruits are stacked like that. Now, what should be the arrangement? So that is the arrangement of spherically shaped fruits is efficient in terms of optimal density? That is, does this packing result the maximum number of arranges? Then what should be the proper arrangement? Well, how can we eliminate the gap? So this is talking about a famous sphere packing problem. It's very interesting. You just Google it, you will find plenty of articles on sphere packing problem. It is also given by Kepler. And this sphere packing problem, when you discuss, there is a tremendous intuitive connect that so far we discussed about tiling in 2 dimension. Now we can move to 3 dimension. And as this each tile is defined as a topological cells, we don't mind going to any dimension. So there is an ample opening of research possible in this tiling field, because you take the reference of 2-dimensional research work, give more and more results about the any n-dimensional space or Euclidean space. With that, I have come to almost end. That is the characterization of the symmetric group of pentagonal lattice tiling. Even these tiles can be treated as lattice. And you have seen I have shown in one of the picture here, the flower, hibiscus flower. This hibiscus flower, when you take, why always shape is like that? So we can talk about the geodesic pattern. Even we can talk about the hyperbolic geodesic patterns. So some of these problems, my student, Mr. Girish and my student, he is working with some of these problems. Anyone are most welcome to take up these problems, and you can always, if you need any kind of contact or any kind of support or help from me, you can always come to me. At the end, I must acknowledge that these are the few papers which has been left and right used. In fact, left and right copied also. Some of things I have taken from those papers, because drawing this is too difficult. So some of this I have drawn, some of this I have taken from these papers. Mainly I was mentioning, my dear, this Gardner paper. I'm done. This Gardner paper and this Zong paper, this Sugimoto, I was showing that. And I must thank this gentleman. He is Professor C.S. Aravinda. And whatever I have explained, it is all started by one of his public talk. It's called Copy with Curiosity, organized by ICTS, International Center for Theoretical Science, in Bangalore. It was almost 3 or 4 years back. His talk is available in this YouTube. You can anytime refer that. You'll find almost similarity in my presentation. I have been inspired by his talk, and I am a student of this Arvind sir. I'm a big follower of Arvind sir. And of course, this magazine also, I have copied many things from this magazine in this presentation. That is all about today's presentation. Anyone you are interested to study more about this, you can always communicate to me. You can contact me. That's all from my side. Stay at home and stay safe. Thank you very much. Done. Dr. Devashish, over to you.
Thank you very much, Anirban sir. And it was really interesting, and it appears from the comments by the participants as well. So we'll start with the question answer session.
Yeah, sure.
Before that, I'd like to display this.
Shall I stop this sharing?
No, it's okay. You can keep it. Somebody might want to see your presentation again during question. I have kept it backstage. I have kept your presentation backstage. So this is one comment from one of the participants.
Yeah.
You can see it on your screen.
No, I don't see anything, because I see only the presentation.
Oh, okay, then you can just click on stop sharing. You will be able to see the screen, and yeah.
I think end shows, like click end show.
No, not end show. Stop sharing. There is an option called stop sharing.
Yeah, but what happened? I just hided that because it was coming in between.
Oh, okay.
No problem. Yeah. I think.
Yeah.
Is that okay?
Yeah. From my side, it's okay. Are you able to see me?
Yeah. I can see. Sure.
The comment on the screen.
Yeah, I can see. Joe's
Yeah, yeah,
Jess
yeah.
Francis.
Yeah,
Okay.
that's for you. Okay, so we'll take up some questions. We'll start from here. We have several questions here. Before that, I think
Thank
Bishwajit
you.
sir, Manjil, I think they left or they're not connected right now. Okay, if they want to get connected, we'll take up their questions as well. So let us start from this one question here. Hmm.
Oh, thank you to Manjil because myself and Manjil, yeah, that's nice.
Oh, Manjil is there. Okay. Okay, Manjil, yeah, you have any questions? You can unmute yourself and switch on your video also.
Yeah, so thank you, Anirban, for the very nice talk. I really enjoyed it.
Thank you.
And it was nice to see Escher's painting. So I visited Escher's museum in Hague several years
Your
back.
video is off, I
Oh,
think.
lucky you are. Lucky you are.
Yeah. So I had a question actually. So as you know, probably that Escher's work is related to some of the work of George Polya on group theory. So do
Yes.
you can you also like say something about that? So I have very little idea about that, but if you can just elaborate a bit,
Yeah.
if you know.
Actually, to be very honest, I wanted to discuss that because you can see in my presentation, I deliberately avoided any mathematics. I mean, higher mathematics. Basically, I just use the term, no, the periodic and aperiodic. So when you talk about that translation or transformation, when you talk about this transformation, basically, if you construct a group of these transformations, okay, you will the situation of the symmetric group will come into picture. So if I am not wrong, probably Escher has taken those symmetrical group structures only. Probably he did not work with the asymmetrical structures. I'm not very sure about that. But generally what happened, whenever we talk about the tiling area, if the each set, if you take as an element or each tile is an element and you do the transformation from one tile to another tile, like something we study symmetric group or permutations group, like that, if you construct a group of these transformations, what exactly you come across? You come across a group structure by the operation between two functions or two transformations. So if it is a symmetric group, probably Escher took the symmetric group nature. I'm not very sure whether he worked with asymmetric or not, but definitely symmetric group plays a major role. And there is another lattice structure. I deliberately avoided this. In fact, my student is working with that area, particularly lattice structure of tiling. So I hope I could answer to some extent about your questions.
Thank you. So we should talk about this later then.
Sure. You finish your talk tomorrow, we'll catch up. Oh, you have a fan here, Manjit.
Oh no.
So I'm big fan of Manjil sir. So tomorrow all participants will get to listen to Dr. Manjil Saikia at 4 p.m. So I'm also looking forward to his talk. Okay, so Manjil, shall I take up other questions now? Yeah.
Sure.
Okay.
Sure.
So I'm putting you backstage. Yeah. Okay. So we have these. Okay. So this is one question probably, sir. This is from Ruhul Alam. Yeah, he is my student. Sir, does all polygon or probably or are all polygons monohedral?
Okay.
Yeah, you can see the
See,
question.
if good, thank you, Rahul. Thank you, Rahul Alam, I think, right? Yeah.
Ruhul, yeah.
Yeah. See, if you talk about the monohedral, the moment you talk about a polygon, you can always club different polygons to create the tiling. It is your wish. When you club different polygons to tile, naturally what happened? You are no more in the scene of monohedrality. Because what is monohedral? All tiles are of same size and same shape. Now, actually, it is to some extent easy. Na? For example, I'm drawing one polygon like that, and I can bring another polygon of my wish. Let it not at all be same. The question is, when you talk about the monohedrality, if you take any polygon and you want to tile by only that kind of polygons, that has to be monohedral, but unfortunately that itself, right? So first of all, you decide the structure. Structure is just to say a pentagon, A B C D E. So if ABCD is a pentagon, you do whatever tiling, it has to be done by same ABCDE pentagon. It can be regular, it can be irregular. Now, taking your question, does all polygons monohedral? The moment you go to polygon of 7 sides or 8 sides, it does not tile after all, right? To tile a plane, we have already seen from Reinhardt's research, side has to be less than or equal to 6. So to answer your question, does all polygons tile? Answer is no. A polygon will tile if and only if it is less than or equal to 6. So in short, triangle, quadrilateral, pentagon, and hexagons, they only will tile if you are in the mono.
Okay. So we can take up another one. This is from Rudra Sharma. What is the real utility of studying this particular topic of tiling?
Okay, good. Okay. Utility of studying tiling is, actually I should say, I don't have that much knowledge to explain, because that could itself create a conference. You know why? I just mentioned something about crystals. You talk about the atomic structures, you have tiles. You go to chemical engineering, you have tiles. In fact, surprisingly, in 2 years, from last 2 years, we are seeing this tiling nature in digital signal processing. Whenever people talk about the traffic of signals, signal trafficking, they are using tiling concept, because tiling is directly or indirectly gives a connection to networking. Probably tomorrow when Dr. Dr. Vishwajit explain, might be networking is there. So in graph theory also these tilings are using. So utility of tilings is just ample. It is us to take up. Directly construction, chemical engineering, chemical structures, and mainly atomic structures, these are huge.
Okay. So we'll take up another one from here. Padmeswar Senapati. Can we draw this type of tiling in MATLAB or Maple or other math software?
We can draw these tilings in MATLAB, Maple, because these are, in fact, I mentioned about Michel Rao. When Michel Rao did more than 731 tilings samples, definitely he did not draw it. Now, what is that? Generally, we people like myself, I'm technically a dull person. I don't know much more about technicality. So whenever question of drawing comes, I use maximum origin to draw this. But if you go to this MATLAB or Maple, what happened? You need to code it, and you can immediately generate infinite number of tiles. So 100% you draw it in MATLAB. In fact, MATLAB is one of the obvious parts for drawing.
Okay. So let us go to another resource person, Vishwajit sir, who is there with us. Sir, can you hear me? If you have any questions for
Yes,
anybody?
I can hear you, but my camera is, I cannot connect because I am connecting it from my desktop due to some network issue.
Oh, okay, it's okay. We can hear you. You can.
Am I audible?
Yeah, yeah.
Yes, sir.
Okay.
Yes, Vishwajit.
Anirban, thank you for this wonderful lecture. Actually, it was so refreshing. Means without going into mathematics, anybody can understand, and so appealing from presentation point of view. It was a nice presentation as well. In fact, I know that you are a good presenter, but you have improved a lot now. Seems there. So, in fact,
Thank you.
I never gone to means this side of mathematics, tiling side. It's really new for me. But what I observe, a small observation, is that why there's only 15 tiles for pentagons. So if you look into 15, the pentagon can be divided into 3 triangles, and then 3 into 5 gives you 15. 15 has two prime divisors only, 5 and 3, and all this actually maybe one side of the story.
Yeah. Now,
My observation, quick
yeah,
observation.
yeah. No, that is what actually I was trying to, I told in the beginning that if I can instigate that thinking among someone, I mean, I should consider myself successful, because, these triangles we see, pentagons we see, these are not that a complicated figure I should draw. Then why only this? Now, to answer this best is that someone just randomly, it can be just as a good mathematical time, or you can say mathematical time pass. Just you draw a tiling by pentagons. You'll be surprised to see that this pentagon will be one among the 15. And that's why the work, I mean, I remember to answer this question, I think it is very apt. One of our professor, who is no more, Professor Pranay Nath Chaudhary, he was the principal of GC College. The sir was teaching something on real analysis. I remember it's on Riemannian integration. And after doing that proof, I told sir, it is just obvious. I mean, why to spend so much time to prove that? And so what sir answered, no, I'll never ever, I think, forget it. He told that, Anirban, Socrates once told, the hypothesis is so obvious, it took 75 years to prove that obviousness. So this tiling, that's why it is one of the open problem for such a long time, and that is why it has been so interesting. Because why 15 pentagons? Why can't we have more than that? But unfortunately, we don't have. And till 2017, people did not believe also. Because of Michel Rao, I can say we don't have. If it was 2 years back, even I could have told, yeah, we should keep searching. But there is always a lacuna. Michel Rao has proved it using completely programming basis. There was still no mathematical proof that this 15 is the last. So maybe by God's grace, something will happen to us.
Yeah.
Okay. So, Bishwajit sir, should I move on to other questions? Hello? Yeah. Should I move on to other questions, sir?
Yes.
Yeah. Okay. I'm putting you backstage. Yeah.
Thank you, Vishwajit.
Okay. So we have another question here, which will show up on the screen. Pritam Sen, he is asking, can tiling be created in 2, 3, or more dimensional space?
It can be, it should be, and it is actually. The moment you come to chemical crystallizations, you are no more in 2 dimensions. And that is where the higher mathematics come into picture. The moment you go to 3 dimension or any other dimensions, it is almost impossible, like that what I did today presentation, drawing and showing. It is impossible. You need a solid geometrical tool, which is nothing but topology. So that is where we all mathematicians come into picture about tiling. And the present research work is actually on that only, higher dimensional space. Yes, to answer your question, Mr. Pritam, it is, we should tile for any number of dimensions.
Okay. So your lecture has inspired probably many of the participants. So we are getting nice comments. So there are other questions as well. Yeah, this question. This is also from Pritam Sen. Is there any rotational or inversional effect in tiling?
Yes, it is. That is what called periodic and aperiodic tiling. See, when, for example, if I can show you something, give me a minute. I just searching for some squares design. Okay, probably I have this. Okay, so if you see, this is a rectangle. Now I'm shifting it towards left. I mean, because of this left is right. Oh, okay. Now if I shift it towards this, if I shift it towards that, or if I shift it up and down, these are called non-parallel shift transformations, because this and that, they are not parallel, right? They are intersecting. But if you are maintaining this kind of rotation transformation, this is called periodic transformation. Whatever tilings you have seen of these 15 types, all are periodic. But what happens if I take this square and you rotate like that? It becomes aperiodic, and that is what the Penrose tiling come into picture. So there is rotational, there is inversional effect in tiling, and probably, yeah, Dr. Manjil Shaikya was asking, some of that group structure. The moment you rotate, all these are nothing but transformations, and you can create a group. It's a wonderful study ahead. So in precise, your answer is that yes, there is rotation, there is inversion effect in tiling. Very much it is there. It is very important. Good question. Thank you.
Thank you. Okay, so let us move on to this question. Janak Raj Joshi is asking, is it possible to tile the plane using only regular octagons?
No.
No. Only pentagon you said, no?
Regular pentagon also will not do. If it is regular, it is only triangle or square or hexagon. That's it. Nothing else. Octagons means how much it is? 8 minus 2, that is 6 by 8 into 180. Complicated calculation here. I mean 6 by 8 into 180, how much? Probably 144? No. 2, 3, 4. Yeah, 135. If it is an octagon, it is 135 degree. Now 135 you bring together, you already got 270, remaining 90 degree. That will not be supported by an octagon. So you can't do that.
Okay. There is another question from someone with the username clash with Roman. Can you tell the polygon or pentagon or hexagon example in our human body? I'm not clear with what.
Yeah, when I'm not clear.
Okay, let us go to another one. Okay.
Maybe to answer his question, I may try to answer. Talking Euclidean geometrical figures. The human body is not Euclidean. I mean, it's irrational. I mean, not come under anything.
Okay, so this question was already asked. Is it possible to plot this tiles? Yeah. So we can skip this. This was already answered. And yeah, someone's. Okay, yeah. So this is another question here, which you may take up. It's from Roosevelt. Sorry, your presentation is. Yeah. What about Sierpinski triangle and its pattern? Can you say something about it and in which type of tiling it will belong?
Right now I don't know about it. I don't know. What about the Sierpinski triangle?
Yeah, it's Sierpinski triangle. I heard it in topology, or there is another branch. I forgot the name of that branch. Fractals, probably, is it?
I think my students, they are also, most of them who are in this field, they're working. Please note down that even no, sorry, I don't have answer for that.
Yeah, you may note it down. And, okay, so we have another.
You can send me a mail, the last person. If I get answer, definitely I will let you know.
Yes. You can send him a mail. His email address is already being provided in the slide, right?
Yeah.
Okay. So we have another question from Shomabo Chakravarti. Shomaboda. We know that there are two types of polygon, convex and concave. Here you have considered only convex. Can we take concave polygon, that is one angle is more than 180 degree?
Yeah. Thank you very much for this question, because that itself leads to many research problems. Yes, we have restricted completely in convex domain, but we can always do. Unfortunately, we don't use the term concave. We say non-convex, because there is a difference between non-convex and concave. But there is another ample amount of research is going on, and it should be taken up, because I took too much time in the previous parts. So in the scope of research, I did not discuss, but actually I thought I'll discuss about this research possibility is non-convex thing. Yes, it is possible, and it has been happening.
Okay. So we have another question here. It's probably not, it's outside today's topic. Can you explain relation between geometry and topology, please? So maybe you can think of making a video and uploading it in YouTube later. Probably. Okay. So okay. So let us take a general question from Rudra Sharma. Why are mathematicians so much interested in these abstract things which involves symmetry?
Why are mathematicians so much interested in these abstract things which involves symmetry?
Because abstract things find application after hundreds of years. Think of number theory. Number theory is now hugely used.
And
in
it is not only mathematicians. Now everybody is interested to find the symmetry in the abstract things, right? Look at the life going on now in this pandemic situation. It's all abstract. But people are trying to come out with vaccine. That means they're trying to get some symmetry, some logical interpretations, or logical conclusions. So why to target mathematicians alone?
No, actually, yeah, I'd like to add here one thing. In the beginning, when I planned this international webinar, I was planning to present a session on those Reed-Solomon codes, then RSA encryption algorithm. So where the applications of number theory and algebra are very much visible, and even the concept of the fact that it is very difficult to factorize large numbers. This simple fact is used in this coding theory, RSA and algorithm. It is very difficult for supercomputers to factorize large numbers. So one might often people might have questioned that why, what is the use of factorization? Why we are studying number theory? This is why we have been studying, and mathematicians have been studying it since thousands of years. And now in the world of computers, these are finding applications. And the search for large prime numbers is actually one of the reasons, or one of the motives, or is inspired by those cyber security and coding theory and all. Larger and larger prime numbers are better used in the coding theories.
You see, Dr. Devashish, that Fermat, 16th century, he has done Fermat's theorem.
Yes,
That's why today we have all the security, the coding and everything.
Yeah,
right.
He developed
This is amazing. This is amazing.
Even mathematicians, when started solving this problem, new branches of mathematics originated just by trying to solve those problems, those abstract problems. So that is the beauty of abstractness in mathematics. Okay, so I think we can take another question if it's there. We like to know the mathematics. What is this? Is it a question? We like to know the mathematics, though I am a student of applied maths. Yeah. Okay, so it's. Let me see.
We'd like to know the mathematics. I'm not clear about the question.
Yeah, even I'm not clear. Maybe it's not a question. It's. Okay. Okay, so almost we have done. Just I'll check my mail. I had put some questions in the mail also. Some earlier comments are not visible. Okay, yeah. So there is one question from Troilokya Mohan Goswami. Please give names of probably he meant books or materials related to this particular topic.
Books on tiling.
Yeah, books on tiling or any material.
Quickly, what comes in mind is that Grunbaum, something I mentioned. This is what I elaborate.
Would you like to share your screen?
But can I show it now? Can I go back to the presentation now?
Yeah, 1 minute. Yeah. I've already added it to the stream. Your presentation is visible now.
Okay.
I think in the reference it was there.
Yeah, I have mentioned only one. I showed it. See this one, Grunbaum and G.C. Shepherd, Tiling and Patterns. In fact, it is available in net also. You don't have to buy also this book. This book, in precise, it discusses in depth. And recently, this Zhong, the Chinese mathematician, Zhong also has written a very nice book. But I have not come across anything very fundamental or elementary on the tilings rather than research papers. But Grunbaum is a quite good one to read. But still, the way the books are written, from the first chapter itself, they go to lattice, they go to group geometry. So it's quite background required.
Okay, so there is one more question. Just now it popped up. Can you see this?
I can see.
Has there been any on intersection of fields like graph theory with tiling? Graph theory looks like a weak candidate, but given its roots in topology, I'm curious. Okay.
Graph theory is not a weak candidate, But of course, graph theory, you see, the advantage of tiling is you are talking about the full space, right? You are talking about the polygon, means you are not discussing only about the edge and this, even the inside this. I mean, I have not discussed about the topological definition of the tiling part. If you look at the topological definition of tiling part, how it is defined, that each, if you take, what is called, if you take each tile, then the interior, what you say, that when you take two tiles, intersection is a vertex or disjoint or a common edge in entire. But if you talk about the topological point of view, it is like that the interior of the topological cells is either disjoint or having a single vertex. So this is just an advantage. I will never say graph theory is a weak candidate, but definitely we have little bit advantage in tiling because we are discussing about the full surface here. Probably graph theory, you don't talk about the full surface, or I'm not so authentic person to talk about the graph theory. But yeah, it's not weak. It's not weak. And there is a connection. 100% is the connection, no doubt.
Yeah, in fact, Vishwajit sir was also looking for that, and he was particularly interested in your presentation. So
who? Sorry, I missed that.
Bishwajit Dev sir.
Yeah, sure.
Working on graph theory, and he was quite interested about your presentation. So probably tomorrow also we can hear from him more about this. So as of now, there are no questions. Bishwajit sir, if he is still there, would you like to add something, Bishwajit sir?
Yeah, he's there.
The number of questions came up for the session itself speaks how nicely he presented a topic and how popular the topic is. It's really commendable. Congratulations that you have been able to penetrate to so many students' mind, particularly. Okay, and that was the aim of this webinar, to give students some areas, exposure to some areas where mathematics is visible. And this is probably tiling is one area where anyone can see mathematics is visible.
Yeah.
Thank you, Anirban.
Thank you, Vishwajit, for such a nice words.
Thank you, Vishwajit sir. We are looking forward to your presentation tomorrow.
Tomorrow we'll connect.
Yeah, I'm putting you backstage. Okay, then on behalf of the Department of Mathematics, I would like to thank Anirban sir for such a wonderful presentation, and I am sure the participants have enjoyed it. Just right now we have another comment. Okay, so for the participants, I would like to say some of you are asking that the name of the institute is not there. So for that, I'd like to mention that in the registration forms that we have received, many of the participants did not mention their name of the institute itself. Say they wrote something like Silchar, Guwahati. Okay, so for those candidates, you may not be able to find the name of the institute in your in the feedback form. So just send me a mail. I'll be able to recognize what is the problem. Okay, so that's not a big deal. And some of you may not find your name also, because the same problem, so some candidates did not fill up their names. They had just written the names as Mr., Miss, Doctor, without writing any name. They have just written the prefix. Okay, so if you are having such troubles, you can just mail me your details. I'll just check and verify. Okay, and certificates will be presented only to those who had registered and who are attending the lectures. Okay. And yeah, some of you have written that feedback form is not working. Okay, I'll get back to that, and I'll post the feedback link in the comment section as well, not in the live chat box. I have already posted in live. I will also post it in the comment section of the of this YouTube video. You can visit it after some time. You will get it. Okay. So Anirban sir, thank you very much. We are ending the broadcast now, and for all the participants, we'll meet you tomorrow at 9. We have the fourth session by Mr. Joydeep Das from TCS, Florida, USA. So till then, goodbye for today. Yeah,
thank you very much from my side. Thank you very much
Yeah.
from my side. And I just want to add again is that, to speak something in your own college platform, wherever you go, speak, give talk, or write anything, to do something or to be a part of your college, your own department is the best thing as you can aspire. So
Yeah.
anyone, in case you are interested or you have any doubts, please feel free to contact me. Consider me your senior from the same group. Say, if I mean, men who are from the DC college, I'm telling them, please feel free to contact me, communicate me, and you have a wonderful teachers. You have this thing, and any other participants, whoever here, any kind of doubts, please do get back to me. It will be really pleasure to answer your doubts. Thank you very much.
Yeah. Thank you, sir. So I am closing the broadcast now. Thank you.